You want to estimate some quantity or other, because as I said, analysis deals with quantitative aspects of scientific investigation. So at given any number, I am out to estimate something or the other. So I want to estimate this. What it says is, no matter what you see, a real number you take, mod a minus b is less than or equal to a minus c plus c minus b. It is true for every c. Okay, this way of thinking is somewhat dynamic. You will understand better. Now, what does it tries to say? If I want to show mod a minus b is very small, then I have to choose c so that c is very close to a, therefore mod a minus c is small, and c is simultaneously close to b, therefore mod c minus b is also small, therefore I expect mod a minus b will be small. This is the trick you have to learn. This is the best way of understanding triangle inequality, not like just like mantra, chant it, then that's true. So this shows I have to make a smart choice of
Yes, sir. Yes,
Yeah.
it's start percent.
So I'm sorry if I forgot. So let me quickly go through. If a and b are real numbers, okay, as I said, analysis is a quantitative aspects of scientific investigations. So given two things a and b, I want to say how close they are. Mod a minus b, I have to estimate. Okay, and what it says is the triangle inequality. The way I look at it is, no matter what c it shows, mod a minus b is less than or equal to mod a minus c plus mod c minus b. So if I want to show mod a minus b is small, then I have to make a smart choice of c, so that mod a minus c is also small and simultaneously mod c minus b is small. That will make mod a minus b small. So this c, I call it the curry leaf. All of you know karivepla, right? In sambar, rasam and curry, everywhere we put this. Okay, that is to add aroma, but most often 99% of the people don't eat it. They just take it out, right? The same purpose it does. Okay, so it just serves the purpose of estimating mod a minus b. Okay. Think of it triangle inequality like this. You will see, yes, something like 60 to 70% of the time in analysis you are doing this. Okay, the only thing is now you have a principle, you have a tool, so you understand this is the tool I am using. It's not like simply understanding the proof, but you will understand why I want to do certain things. Let me show its power of thinking like this. So let us say I have a sequence xn of real numbers, real sequence. Okay, right. So let us assume that xn is convergent. It converges to x as well as it converges to y. All of you know, then uniqueness of the limit should say x equal to y. Yeah. To quickly recall, when do I say xn converge to x? I don't write like limit n tend to infinity, etc. Okay, I write only this way. Okay, what is the meaning? That means give me any epsilon positive, I can find a natural number n, so that for all k greater than or equal to n, xk is very close to x. That is mod xk minus x is less than epsilon. That is all my xk approximate x after certain stage, namely when k is greater than or equal to n. This
Sir,
is the way we do that. Yeah.
excuse me, sir. Sir, your audio is breaking.
That means it's I think
Hello, sir. There is no problem in the audio. I think there may be some network issues. Yes.
it's the same. But if it happens too often, just let me know. Okay.
Okay, sir.
Just wait for a few minutes. Usually it stabilizes, and after 3 minutes, you just tell me if there is the problem still continues. Then you have to think of something.
Okay, sir.
Otherwise, I'll just switch off the second thing. Maybe both are consuming the bandwidth.
Sir, there is no problem in the sound now.
Okay, that's all. Okay, let's hope so. Now, so I have xn converge to x as well as xn converge to y. Then I want to say x equal to y. Okay, this is what I want to prove. Right? Remember yesterday I said in analysis you rarely prove a equal to b. When I want to prove a equal to b, I said I will prove a mod a minus b is 0, and this also I don't prove. I will prove that for every positive epsilon, mod a minus b is less than epsilon. From that I will conclude mod a minus b is 0 and hence a equal to b. Do all of you remember this? See, this is the way analysis works. Equality is proved only via inequality. That is why you have to learn the art of estimate. Don't think of it as inequality. Think of you want to estimate something. So when I want to say mod x equal to y, what should I do? I have to prove mod x minus y is 0. For this, what should I do? I have to prove mod x minus y is less than epsilon for any epsilon you gave me. Given epsilon positive, I have to prove mod x minus y is less than epsilon. That means I have to estimate mod x minus y and show it's less than epsilon. Now how do I do that? See, this is where my curry leaf trick comes. What does it say? Now you have to find some z, a real number, so that mod x minus z is small and mod z minus y is also small, and let's say they both of them are less than epsilon by 2, then I would have got the result. Now can I get it? Yes, because xn converges to x. Okay, therefore for epsilon by 2 there is an n1, so that okay, if k is greater than or equal to n1, mod x minus xk is less than epsilon by 2. And similarly xn converges to y, therefore for the same epsilon by 2 there will be some other natural number n2, so that when k is greater than or equal to n2, mod x minus xk will be less, sorry, mod y minus xk will be less than epsilon by 2. Right? Now what do I want? I want z common, right? Therefore I want a z. I can take, suppose I take k equal to n1 plus n2 or maximum n1 n2. Sometimes students always like this, teachers also always say that, okay, one of those things. If k is n1 plus n2, then k is greater than n1, therefore mod x minus xk will be epsilon by 2. Similarly, mod yk, sorry, mod y minus xk will be less than epsilon by 2. Therefore mod x minus y is less than or equal to mod x minus xk, where k equal to n1 plus n2 plus xk minus y, but each of them is less than epsilon by 2. Please pay attention. This is the simplest way I can explain whatever I was talking about analysis. Analysis means it's a quantitative. For that, quantitative means you should learn how to order relation, okay, less than or equal to, greater than or equal to, inequality, estimation. So when I want to prove two real quantities are equal, a equal to b, most often we will prove the distance between a and b, in this case mod a minus b real numbers is 0. And that also you don't prove equality. You prove by means of, for every positive epsilon, mod a minus b is less than epsilon. Do you see that? That's what I did. And I also on the way I explained how the curry leaf trick works. Okay. So curry leaf trick is a sophisticated way of dealing with triangle inequality. So I will give you about 10 seconds, pause, think, and then let's proceed. So this xk, where k equal to this is our curry leaf. Okay, just for the purpose of estimate mod x minus y, I used it. That's it. How many of you understood? Please raise hand. Some teacher, if gives the number something like 10, 15 or some such thing, I'll be happy.
So more than 15 is now.
Very good, excellent. Good, I'm happy. Now let's look at the same curry leaf trick where it is used elsewhere. Okay, it's a counterpart of this. This is second application of what is analysis about and how to make use of triangle inequality in the form of curry leaf trick. Okay, so let have a sequence xn. Okay, this is again a real sequence. When do I say it's a Cauchy sequence? I say it's a Cauchy sequence if n and m are very large, the distance between xn and xm is very small. This is a very qualitative way of saying. See, when I say this is very large, I don't quantify. And when I say xn minus xm, xn and xm are very close, or the difference between them is very close, I again don't quantify. Do you understand that? This is qualitative. Analysis comes when I make it quantitative. So what does it say? It says that give me any epsilon, there is a natural number n, so that whenever n and m are greater than or equal to capital N, mod xn minus xm should be less than epsilon. See, now I made everything quantitative, because how small they are, epsilon is given, and n and m are very large. What does it mean? N and m are greater than or equal to capital N. You see that qualitative analysis becomes quantitative analysis. That's what real analysis about. Okay, now how do I prove it? So I want to say xn and xm of close, right? Okay, now this is the theorem, which again a very trivial result, but I wanted to illustrate what is analysis about, how the triangle inequality in the form of query leaf is an important tool for analysis. That's the aim of today's talk. Okay, so even if you think you had already seen a proof, you will only know line by line proof. Now you will understand what is really happening. So the theorem is, suppose xn is a sequence, convergent sequence of real numbers, then xn is Cauchy. Okay, this is what we want to prove. Yeah, right. Is my audio okay now?
Yes,
Yes,
sir.
sir.
It's okay.
Oh, okay. So now when I want to say xn is Cauchy, again think qualitatively first. That means for n and m very large, I want to say mod xn minus xm is very small, right? So my curly leaf trick, what will it show on xn minus xm is what I want to estimate. My curly leaf trick says you find some c, so that these are very small. Mod xn minus c and plus mod c minus xm, they are very small. Now how do I find a c so that xn minus c is small? Now let's go back to the hypothesis. What did the hypothesis say? The hypothesis said xn is convergent. What does that mean? That means there is a real number x so that xn converges to x. Right? Now we can make everything quantitative. So I wanted to show xn is Cauchy, so let epsilon positive be given. Right? I have to find a capital N natural number, so that for every n and m greater than or equal to capital N, mod xn minus xm is less than epsilon. So our trick is to find a curly leaf so that means I want to find a c which is very close to xn, simultaneously close to xm for certain m and m greater than or equal to capital N. Where do I find it? Since you said xn is convergent to x, for this epsilon there is a natural number n, so that for every n and m greater than or equal to capital N, mod xn minus x is less than epsilon by 2, right? Because xn converges to x. For this epsilon there is a capital N, so that this happens. Now what should be my c? I take c to be this x. Okay, let x be the limit of sequence xn. Okay, assuming xn converges to x, right? Then mod xn minus xm is less than or equal to mod xn minus x plus x minus xm. This is immaterial of what x you chose, but now I am choosing my x smartly. What is my x? That is the limit of the sequence. Then what do I know? If n and m are greater than or equal to capital N, by this I know this is less than epsilon by 2, and m is also greater than or equal to capital N, therefore this is also less than epsilon by 2. Therefore I got for n and m greater than or capital N, mod xn minus xm is less than epsilon. You see that? Again, we started with the qualitative way of looking at, then we made it quantitative. To prove the quantitative version, we wanted to use triangle inequality, there we used curly leaf trick. If you try to understand, digest proofs like this, you will see mathematics is very interesting, because it makes you think. It doesn't want you to memorize, or it doesn't want you to accept as you would accept religious text. So I'll stop for 10-15 seconds. Please review. If you have any questions, please raise your hand. Please ask, I will explain. Can I proceed? If I can proceed, please raise your hand. If there are at least 15 people who raise hand, I will proceed.
Sir, this triangle inequality condition is exists every time, or it's due to that limiting case of given conditions.
Can you be more precise?
Sir, in every time this triangle inequality condition is existed,
Yeah.
or it is comes from the conditions that given. In some cases,
No, you have to focus your question. Okay, this
yes,
is
sir.
that's why I keep saying. Unfortunately, our education system wants us to answer, but the real thing is asking questions. We have to train our students, our generation, our people, citizens of the country to ask questions. Okay, not to simply answer. Okay, asking the correct questions and making it more and much more precise is the best way to understand science. Not science, yeah, any acquisition of knowledge. Can you please repeat your question?
Sir, every time the triangle inequality condition is there, sir.
What do you mean by
We
triangle
cannot
inequality condition is
suppose.
there? What do you mean by
Suppose
triangle
there are.
condition? See, triangle inequality says is something thing. It's something like did you ever ask what is a plus b whole squared, a squared plus 2ab plus b squared? Did you ask? It's always true, right? It's an identity for whenever a and b commute. Like that, when
Means,
you give me two thing, if I have a metric, I think from your photo, I think you're a teacher or senior. So I am just saying, okay. Any metric space, that's a true thing, right? Distance between x and y will always be less than or equal to distance between x and z and distance between z and y, immediately of which z you chose. The trick is teachers will simply write for every x, y, z, whereas I am saying you choose z carefully so that you can estimate. Okay, please think
yes,
about it.
sir.
Okay. Right. Now let's go to a third thing. Okay. So all of you know, given a sequence xn, I'm just trying to stick to basic analysis so that even if for a PhD student analysis, many of the students do not know these things. They have just gone through the proof line by line. They know if necessary they can repeat the proof, but they are not mastered. Okay. So everybody can learn from this. Because I'm saying this is the trick, as I said, 60% of the time in analysis, this is a trick you will be using. Okay. So all of you know what is meant by a subsequence. That is, you have a sequence of natural numbers, so that nk less than nk plus 1, etc. Then look at nk going to xnk, this is a sequence. So this is k going to nk going to xnk. This is a sequence. Okay, but this x and k is called a subsequence of xn. Okay, now what is the meaning of a subsequence converging? That is, when I want to write x and k converge to x, what is the meaning? I only know how to define a sequence converging, but okay, but you all analysis books and textbooks will simply assume subsequent convergence. You understand, but that is why I wrote it like this. Look at this. I have a sequence of k going to x and k. Call this a sequence y, where yk is x and k. Okay, for k, what is a sequence? For each natural number k, there should be a real number. That is a real number yk. What is the real number yk? That is x and k. Now this is a sequence. K going to yk is a sequence. So does it make sense yk converges to x? Yes. right? Because I have defined what is meant by a sequence converging to a real number. Therefore, yk converges to x. If yk converges to x, then I say x and k converge to x. So x and k converge to x is by definition same as yk converging to x. Keep this in mind. This point is except in my book, it's very rarely explained. Not very rarely, it's never explained. So the question I want, this is again a standard theorem on analysis. What it says is, suppose xn is a Cauchy sequence. Okay, and suppose x and k is a subsequence, and assume x and k converge to x. Then you want to conclude the original sequence xn itself converges to x. This is one of the most important tricks in analysis. Most often you want to show some sequence is convergent, you may not be able to do that. What you can show is it's a convergent, it's a Cauchy sequence, and you may be able to spot a convergent subsequence. Therefore, you know the limit of the original sequence xn. Please understand. See, because unfortunately everybody learns a theorem proof, they don't understand it's a tool. Okay, I may have sequence xn. Okay, I want to say it converges to x. I may not be able to do that. What I can do is I can prove xn is Cauchy. Okay, I may not even know what is this x, and I may be able to find a subsequence x and k such that x and k converge to x. Then from these two facts I can conclude x and converge to x. See, in my book I would have given some 3 examples or more in exercises. This is one of the important tricks. Throughout your analysis, if you go to functional analysis also and complex analysis, you will use this kind of trick. Now, how do I prove that? Is the question clear now? I have a Cauchy sequence xn, I have a subsequence xn k, and I am also given the subsequence xn k converge to x. Then I want to prove the original sequence xn itself is convergent, and where does it converge to? It converges to the limit of the subsequence. So whenever you read a theorem, try to paraphrase it in your own language. Try to say it in your own language. Okay, say it in different way. Even if it's wrong, does not matter. Say that, slowly you will understand how to understand a theorem. See that you can understand how to understand a theorem. Proof is not theorem. Proof is a validation. Okay, it's just a validation process. Okay, so I want to prove that. So when I want to say xn converges to x, again remember, when I want to say xn converges to x, that means I have to estimate. Okay, because what does it say? If n is very large, xn is close to x. That is mod xn minus x is small. Okay, this is qualitative version, right? That means mod xn minus x, I have to estimate, I have to make it small. So again, when I want to make this small, what will I do? As I said, I have to find a curly leaf such that xn minus c plus c minus x is small. Each one of them is small, then this will be twice small. That's it. This is the intuition. How do I find such a c? You see that? You are focusing now. Now that you understand what is the tool, now my thinking is very, very precise. I have to find a curly leaf. Now I have to go back to the hypothesis. What did the hypothesis say? Hypothesis said x and k is a subsequence, it converges to x. That means if k is very, very large, my x and k minus x will be small. That's what it means to say x and k converge to x. This is the qualitative version, right? So this shows that if I want to make this less than epsilon by 2, I should choose C to be something like x and k, where k is very, very large. Again, we are being qualitative. You understand? Now the next thing comes. Okay, I may be able to make this less than epsilon by 2. How do I make this less than epsilon by 2? Now that is the next thing I have to use. What is the hypothesis? Xn is Cauchy. Therefore, here I am going to have something like xn minus xn k. I do not know which n and k, but let us assume. But since xn is Cauchy, if n and nk are very, very large, I know this is also small. Do you understand? This is how you learn mathematics, not by just writing proof and trying to say that it's a correct argument. Mathematics is not logic. Logic is needed for mathematics. Okay, so how do I do that? Okay, so now let us make it everything quantitative. Let epsilon be given. Okay, now since x and k converge to x, okay, there exists a k naught, so that for every k greater than or equal to k naught, okay, mod x and k minus x is less than epsilon by 2. Remember, my sequence is yk, which is x and k. When I say yk converges to x, what does it mean? For epsilon by 2, there exists a k naught, so that for every k greater than or equal to k naught, mod yk minus x should be less than epsilon 2. But what is yk? X and k. So this is what you have. Therefore, if k is greater than or equal to k naught, okay, if I take my c to be that x and k for any fixed k greater than or equal to k naught, I am through. You follow that? Okay. So second term I had taken care of. Then this term is less than epsilon by 2. Okay, this is taken care of. Now I have to make sure this is less than epsilon by 2. Now for that, so this equation is not due to me. Somebody seemed to open. Okay. Now think of this. For this to be less than epsilon by 2, what do I need? N and nk should be greater than very large, right? Now again, this is qualitative. I have to make it quantitative. Since xn is Cauchy, okay, there is a capital N, so that what happens? Whenever n and m are greater than or equal to capital N, mod xn minus xm will be less than epsilon by 2. So now go back. So it's very clear I can choose my n to be greater than or equal to capital N. But then I have to make sure nk should also be greater than or equal to capital N. At the same time, mod x and k minus x is less than epsilon by 2. That means k must be greater than or equal to k naught. Now how many of you see there is a problem? See, this is, to make you understand, let me just, right, this is fun to learn. Do not worry about whether you are going to pursue mathematics or not, but try to use mathematics as a kind of exercise for you to learn to think, okay, analytically, critically and creatively. This is what is going to help you in future. Okay, 21st century is going to be knowledge based. Okay, so the most important thing is critical thinking. Let us look at. So I have two things. This is x and k, and this is x and k minus x. For this to be less than epsilon by 2, I wanted k to be greater than or equal to k naught, and for this to be less than epsilon by 2, I wanted n and nk should be greater than or equal to capital N. Notice that here the condition is on the suffix k, here the condition is on the entire nk. For example, my n1, n2, n3 maybe 7, 29, okay, 10 to the power 2, and n4 maybe 10 to the power 2 plus 5 and so on. You understand this? Here the condition says the k may be greater than or equal to 4, whereas here the condition says this particular number itself should be greater than or equal to capital N. How many of you appreciate this? Even those who have seen this may not have stopped to think these things. Please, if you appreciate this, okay. You do not understand 100%. If you think, yes, there is something which I'm understanding, please raise your hand. See, think of this as a game. Don't worry about, mathematics, subject, paper, grade, CGPA, university exam. Don't think of it that way. It's a game. You want to win the game. That's it. How many of you understand? At least partially. So there is a problem. But that's very interesting. Yeah, I'm just waiting. For 10 seconds I will wait. If you think you have some kind of an idea, there is some subtlety which I want to understand, raise your hand. I'm going to explain that. I will wait for a teacher to confirm.
Sir, more than 10 raised their hands.
Very good. I am glad. That's enough. Now this is the most important observation about subsequence. See, if x and k is a subsequence, then we know n1 is less than n2 is less than nk is less than nk plus 1, right? There is something very interesting happens. See, n1 is a natural number, therefore n1 is greater than or equal to 1, right? And n2 is greater than n1, and n1 is already greater than or equal to 1, therefore that means n2 must also be greater than or equal to 2, because it's strictly greater than 1, n1. n1 is at least 1, therefore n2 should be greater than. Therefore, let us look at, suppose nk is greater than or equal to k, I claim nk plus 1 is greater than or equal to k plus 1 by induction. Why? Because nk plus 1 is strictly greater than nk, but nk itself is greater than or equal to k by induction hypothesis. Therefore, nk plus 1 is a natural number which is strictly greater than the natural number nk, but nk is at least k. This implies nk plus 1 must be greater than or equal to k plus 1. So, the important observation about subsequence is the indices nk satisfy this condition for all k. This is the most important fact about subsequence. Now let's go back. So line by line proof, okay, kills a lot of things. So for this to be true, I wanted k to be greater than or equal to k naught. For this to be true, this is a condition. And for this to be true, I wanted n and nk should be greater than or equal to capital N, right? Now remember, nk is already greater than or equal to k by the important fact. Therefore, to make sure nk is greater than or equal to n, what do you think I should do? Can somebody tell me? Are they allowed to open their mic and say? Can they unmute their mic, the students?
Yes, sir. They can unmute.
Yeah. Can at least one student tell me? I wanted nk to be greater than or equal to k. Okay, I already observed nk is always greater than or equal to n. So how can I ensure nk is greater than or equal to capital N? What condition should I impose? You go through any book, these kind of things are never explained. Okay, carefully. So obvious. So if I make sure k is already greater than or equal to n, then nk is greater than or equal to k. Therefore, nk will also be greater than or equal to n. Therefore, now do you understand the subtlety? Here the condition was on n and nk both should be greater than n. Here the condition was nk, that is k on the condition on k greater than k naught. But now I made both the conditions on k. So for this to be true, what all I need is k must be greater than or equal to n. And for this to be true, I needed k to be greater than or equal to k naught. Therefore, if I take n1 to be maximum of n and k naught. Okay. Now for all n and m, sorry, for all n greater than or equal to n1, mod xn minus x will be less than or equal to mod xn minus xn k plus xn k minus x. Okay. Now take to k to be n1. Since k is n1, nk is nn1, that is greater than or equal to n1, and n1 is greater than or equal to capital N. Therefore nk is greater than or equal to capital N. Therefore mod xn minus xnk is less than epsilon by 2. And now next, k is n1 and n1 is greater than k naught. Therefore mod xnk minus x is less than epsilon by 2. So I proved the result. This proof usually in 3 line, 4 line books will write, but you will see how much of analysis is going on, how much of subtlety is involved in this proof. So I'll give you about 20 seconds. Okay, please go through this. So what was the trick? The trick was to make this, I needed the condition on n and nk, and here I needed the condition only on k. So what was the trick we observed? We observed nk is always greater than or equal to k. Therefore I reduce this condition only on k. Both this inequality should be less than epsilon by 2. Both these expressions should be less than epsilon by 2. Therefore I impose a condition on k. That is the subtlety. Okay. So enough of sequences. Now let's do something else. Okay. Let's go back to the original thing. I have a and b, two real numbers. I wanted to estimate this. Then I said choose c in R so that for every c this is true. If I wanted to show this is less than or equal to something, then choose c so that I can show that mod a minus c is also less than something, mod c minus b is less than something, therefore I can conclude. So that is the C correlate. Okay, this has nothing to do with only numbers. Okay, suppose I have two real valued functions f and g. It could be even any set, but many of you will have problems, so let me just take an interval ab to R. So real valued functions, right? Suppose I want to show for every x in the interval ab mod fx minus gx is less than epsilon. You understand this? I want to show this. I will spend some time here, then I will go to its application quickly. You understand this problem? Not for one x, for each and every x I want it to be this mod fx minus gx should be less than epsilon. For which x? For every x in AB. But remember, once I fix an x, fx is a real number a, gx is a real number a, therefore I have to show mod a minus b is less than epsilon. Therefore, this again shows my fx minus gx. I can write it as fx minus some cx plus cx minus gx. This just c is a real number. I am just showing this real number depends upon c possibly. Okay, this is a Curry trick because this is fix x in AB. Okay, now this is a real number, this is a real number. But triangular inequality says for every c this must be true. So if I want to show this is less than epsilon by 2, what should I do? I have to choose a c so that mod fx minus c plus mod c minus gx is less than, each one of them is less than epsilon by 2. Right? I fix an x, therefore this c I may change. If you give me some other x dash, I may choose a c dash. That is why I wrote c of x. It may depend upon, it may even be a function. How many of you understand what I'm trying to say? So C may depend on X. Okay, this is a real number, this is a real number. For this two real numbers, I am choosing a real number C. But if I change this real number, then C will also vary. Therefore, that's why I think of it as a function of X. How many of you understand? If you understand, please raise your hand. Yeah, good. So that means I have to find a function C from don't think of it as a constant now, C to R, so that mod fx minus cx is less than epsilon by 2 and mod cx minus gx is less than epsilon by 2. Okay, now I am writing a C. Yeah, but something much worse can happen, but I will come to that later. Let us use this to prove a theorem. Okay, let me quickly recall. Suppose Fn, F are functions from an interval a, b to R. Okay, let us assume Fn are continuous. So again, let me quickly recall the definition of continuity. If I want to say Fn, F is continuous at x naught in AB, what does it mean? It means if x is near to x naught, that is if mod x minus x naught is small, this is qualitative, then mod fx minus fx is not small. This is the qualitative idea of continuity. So what is quantitative version? Quantitative version says I want to make this small. So what does it mean is give me an epsilon positive, I can find a delta positive, so that whenever mod x minus x naught is less than delta, mod fx minus fx naught is less than epsilon. Do you remember yesterday's first 10 minutes? This is what I explained. F is a scientific process. These are the ingredients. The output is in R. I wanted, okay, if you give me x naught, pure x naught, I'll get a pure f of x naught. That's the outcome. That is the output I want. But I know in reality nothing is pure in the world. Therefore, you may not be able to find x naught. The scientific process F is correct. Okay, through science we know that it is a correct process. If you give me x naught, it will produce fx naught. That's what I want. Okay. So again, if you want to think of it, let's look at this picture. Okay, this is a y naught I want. Okay, this is my thing. This is my f. So if you give me an x naught, then f will the process. If I x naught is input to the process f, I will get fx naught. That's equal to y naught. So I will precisely get what I wanted. But what I know is it's impossible to get the pure x naught. So what I'm willing to do is I'm trying to find any y such that distance between y and y naught. I'm just writing otherwise they are real numbers is less than epsilon. That is, this is much error I can tolerate. I know that you cannot give me y naught, but if you give me y such that the difference between y and y naught is very small, how small? It should be epsilon small. Then I accept your output. Then what will I do? I am the factory manufacturer. I have tried to find an x. So I know if I find a delta, okay, neighborhood around x naught, then you take any x such that distance between x and x naught is less than delta, then I know the distance between fx and fx naught is less than epsilon. If you don't like distance, think of everything as a real number. This is what I want. This is what I explained yesterday. Okay, if this is less than delta, this will imply this is less than epsilon. Right? Okay. Now let's go to the theorem I want to prove. So I have a sequence Fn from AB to R. These are all continuous for every n. And I know Fn converges to F uniformly. I will explain that again on the interval AB. Okay. So what is the meaning of Fn converges to F uniformly? This is a sequence of functions and this is also a function. But what you have learned is I know how to talk about convergence of sequence of real numbers, right? So the standard trick in mathematics is whenever you have a new problem, you try to reduce it to a problem which you already know how to deal with or your solution, or whether you can make use of that result. Are you following what I mean? I know how to deal with a sequence of real numbers. Therefore, what I do is fix any x in AB. Then let's look at Fn of x. This is a sequence of real numbers. Fx is a real number. So what I can ask is whether this sequence of real numbers converges to Fx. Okay. Then that is called pointwise. Because for each point, x is a point in the domain. For each point, this sequence of real numbers must converge. Okay. So for uniformity, what I want is, so for this, what does it mean? There exists an epsilon positive, so that there exists a capital N x. This depends upon, this sequence depends upon x. Therefore, the natural number n will also depend upon x, so that for every n greater than or equal to nx, mod Fn of x minus fx is less than epsilon. Right? When I want to say it's uniform, this n should not depend upon x. The single n should work for every. Okay, this should be true for every x in the interval AB. So let me write it for ready reference. Let me say Fn converges to F uniformly on the interval AB. Now we are giving a quantitative version. Give me any epsilon positive. There is a capital N, a natural number, so that for every n, let me say for every k greater than or equal to n, and for every x in the interval AB, mod f n of x minus f of x is less than epsilon. Earlier, this is a sequence of numbers, this is a sequence of numbers, therefore this n may depend upon x. But what I want is for every x, the same number should work. Okay. Now what is the result I want to prove? The result I want to prove is if Fn converges to F uniformly and Fn's are continuous on the interval AB, of course, then the limit function, this F is called the limit function, F is also continuous. This is the theorem. So try to understand this. I have a sequence of functions and each one of the functions in the sequence is a continuous function on the interval AB. And what do I know? Fn converges to another function F uniformly. Okay, what is the definition of uniformity? This one. You give me an epsilon, this is a quantitative version. Give me an epsilon positive, I can find a natural number n, so that for any k greater than or equal to n and for every x in the interval AB, okay, this sequence of real numbers uniformly less than epsilon. Okay, I do not spend much time. You can look at my book. There are a lot of examples and pictures so that you can appreciate this notion. This is a very important notion and many students have difficulty with this, so please learn this thoroughly. Okay, now I want to prove f is continuous. So how do I prove it? So fix an x naught in AB. To prove f is continuous on AB, I have to show f is continuous at each and every x naught in AB. So fix an x naught. To prove f is continuous x naught, what should I do? I have to say if x minus x naught is small, I have to show fx minus fx naught is small. This is a qualitative way of saying continuity. That means I have to estimate mod fx minus fx naught. So I have to estimate this. Yeah. So what do I want? Let us make it quantitative. This means you are going to give me an epsilon positive, then I have to find a delta positive, so that whenever mod x minus x naught is less than delta, of course x etc. are in AB. Okay, then mod fx minus fx naught should be less than epsilon. This is a quantitative version, right? So what did I say just now? I have to find a c so that fx minus c plus c minus fx naught is less than epsilon. So I want this to be less than epsilon, therefore if I make sure this is less than epsilon by 2, this is less than epsilon by 2, it will work. But again notice that what did I do? This c will depend upon x. So given fixed thing, so I have to find a c. How will I do that? Now this is where I have to make use of the fact my function f1s are continuous as well as the sequence f1 converges to f uniformly. So let us look at, I know fn of x naught converges to f of x naught because f1 converges to f uniformly on AB. This implies fn of x naught converges to f of x naught. Therefore, what does it say is here the c I can take fn of x naught minus fx naught. Do you see that? The c I can, this is my curry leaf. So if n is very large, then since this convergence is uniform, fn of x naught minus f of x naught will be less than epsilon by 2. Will be small. Let us simply say qualitative. If n is very large, then fn x naught minus f of x naught will be small. This is because of convergence of the sequence f1 to f. Convergence of sequence fx naught to fx naught. Please understand this. There is a subtlety. That's it. So I found a c. But then let me repeat. So that means I have fx minus fx naught is less than or equal to fx minus fn of x naught plus fn of x naught minus f of x naught. Okay, this is equality, sorry, but you will see something I have to do further. See, this is f of x minus fn of x naught plus fn of x naught minus f of x naught, right? So if n is very large, I know I can make this less than epsilon by 2. But then here there is something nonsense. You see that this is f of x, whereas this is fn of x naught. Okay, I do not know how to compare f of x and fn of x naught. How many of you understand this? So there is a problem. So this one I again have to write it. Okay, I should estimate. Okay, let us take a digression. As I said, analysis is quantitative. Okay, it deals with the quantitative aspects of science. Now, as I said, if when I want to show a is less than or equal to alpha, right? Most often analysis may not be able to prove a is less than or equal to alpha. What it will try to show is a is less than or equal to b. Maybe I can prove easily b is less than or equal to alpha. Sometimes even that I may not be able to do. But then from the expression for b, I may show that b is less than or equal to c. Then I know c is less than or equal to alpha, and hence I will conclude a is less than or equal to alpha. Do you understand that? My original aim is to prove a is less than or equal to alpha. I may not be able to do it correctly. I may not know how to do it. But what I know is it may be easier for me to show a is less than or equal to b. If b is less than or equal to alpha is easy to see, then I am through. Suppose not, then I will again try to see b is less than or equal to some other quantity c. Then I may be able to show c is less than or equal to alpha. If it doesn't happen, you have to find a d also, and so on. Okay, this is the very important trick in analysis. That's why you will see in analysis book there will be a lot of inequalities. The reason is for that. Let's go back. The diagram is over. Let's go back. So I saw mod fx minus fx naught is less than or equal to this, because this way I can make sure this is less than arbitrarily small. Okay, very small. Now I have f of x minus fn of x naught, but then this x and x naught are different, and this is f, this is f1. There is a slight problem. Now how do I deal with it? This is where I use the trick. I will say this fellow is less than or equal to some other guy. So let us look at mod f of x minus fn of x naught. Okay, I know how to do this, equal to mod fx minus fnx plus fnx minus fn of x naught. Again I am using curly leaf trick, triangle inequality. Do you see that? Mod fx minus fnx plus fnx minus fnx naught. This is my curly leaf now. See. Why do I know? Because fn converges to f uniformly. Therefore, for if n is very large, mod fx minus fnx will be small. Very good. Now what do I do here? So far I never used the fact fn's are continuous. Continuity of fn I never used. Now I can use it. You see that this is the same fn, this is also fn. If x is very close to x naught, fn of x will be very close to fn of x naught. Therefore, this also I know how to make sure this is less than epsilon by, make it epsilon by 3, epsilon by 3. Therefore, the earlier one also let me make it epsilon by 3. Okay. Please understand, I am just dealing with how mathematicians think through a proof. When we write a proof, it looks very crisp and clear. You can only check line by line. You can check logically it is correct, but you may not know how the proof was arrived at. What I am trying to show is how a typical working mathematician will think through a proof. It will be overwhelming. Do not worry about it. Just follow. As I said, anything which you learn, even when you try to start talking Malayalam and at the age of 2.5, you would have difficulty. Right? Slowly you picked up, but you never gave up. You understand? You just keep trying, then you will get. So the first thing is you have to understand 20-30%. Slowly it will improve to 40, 50. Slowly you will understand. Don't expect that you should, when you learn something, you will understand 100% on the very first instance. It never happens, even for a genius. So it's a myth. The teacher is so good, when he explains, I learned everything. Okay? Either you are deluding yourself or teacher is trying to hoodwink you. So let us go slow. Let me go back and prove what I have done. So I wanted to estimate f of x minus f of x naught. My thing is, if x, this is close to 0, then I want to say this is also near to 0. So what was the trick? I said I will split it into things, fn of x and plus fn of x minus fn of x naught plus fn of x naught minus f of x naught. So this is what we are arrived at. Again, it is qualitative. This is immaterial of which n you chose. For any n, this inequality is true. For every n, this inequality is true. But what is the idea? The curly leaf trick says you choose this n carefully now. Right? How will I do that? I want this to be less than epsilon by 3. I want this to be less than epsilon by 3. I want this to be less than epsilon by 3. Let us concentrate on this. Each fn is continuous. Therefore, if I want to make sure this is less than epsilon by 3, okay, I can choose a delta so that whenever mod x minus x naught is less than delta, this fellow will be less than epsilon by 3. So continuity is what is needed to prove this. Right? Now I want to make sure this is less than epsilon by 3. That means you see that now it's x naught is fixed. Here x and n is fixed, but x and x naught vary. Here x naught is fixed, but fn and f, the functions are different. Now what do I know? Fn converges to f uniformly. Therefore, whatever x you give, in particular it may be an x naught, it may be any x which is near to x naught. So I have an x naught here. My x may be something here. Yeah, my x may be anything here. You see that for every x, I want this to be less than epsilon. That is where the uniform convergence takes place. Here it is okay. This is only one point. Okay. Therefore, for epsilon by 3, I know there exists an n, so that for n greater than or equal to capital N, mod fn of x minus f of x is less than epsilon by 3. This is for every x in the interval AB. In particular, for every x in the interval around x naught and as well as for x naught, this term will be epsilon by 3, this term will be epsilon by 3, provided my n is greater than or equal to capital N. Now I don't want to keep saying which this n is greater than or equal to capital N. What I will do is I will freeze. Okay, I'll choose only one n. So I will write it as f of x minus f of x naught is less than or equal to f of x minus f capital N of x plus capital Fn of x minus capital Fn of x naught plus capital Fn of x naught minus f of x naught. Okay. Now look at this. By uniform convergence, whenever n is greater than or equal to capital N, in particular for capital N, for every x. Therefore, for any x in the interval AB, this will be less than epsilon by 3. For x naught also, it's less than epsilon by 3. That's so. These two terms are made less than epsilon by 3. Each is less than. Now, how do I make sure this is less than epsilon 3? I want to make sure this is less than epsilon by 3. How do I make it? That's very easy because Fn is continuous at x naught. Therefore, there is a delta positive, so that whenever mod x minus x naught is less than delta, mod Fn of x minus Fn of x naught is less than epsilon by 3. So I made sure the middle term is also less than epsilon by 3. Okay, so we are arrived at a proof. Let me just give you a typical way the proof is written in a textbook, but I just want you to go through this about 20 seconds. So let us go slow. What did I want? I wanted to write fx minus fx naught. Then I know fn of x naught and fx naught will be very close, so I just introduce. That is my first curry leaf. So I wrote it as less than or equal to mod fx minus fn x naught plus fn x naught fx naught. So this term I can make sure less than epsilon by 3, epsilon by 10, I don't care. I can make it very small if n is very, very large. Okay, this I can make sure. But then here there is a problem. This function is different, the values are also different. Okay, so there is no way I can make sure this is less than something. So what do? Again I use a curry leaf. What do? I know fx is very close to fn of x if n is very, very large, and then fnx is very close to fn of x naught if x is very close to x naught. So these are the two facts. Therefore, what do? So I introduce that. You see that fn of x. If n is very, very large, this will be less than epsilon by 3, and for a fixed n, continuity will tell me. This is the basic idea. So 10 seconds I will keep quiet. Please go through this. How many of you at least understand 20 to 30% or more? Please raise your hand if you have some kind of idea what is going on. Are there any students who raised hand?
So some 15 students raised a hand.
Wow, that's a lot. Good. Very good. Now let's write a textbook proof as you would see in a textbook. You will see how simple it looks, but then whatever thinking went in my head or in anybody's head is never explained. Okay. So let epsilon be given. Okay. Since Fn converges to F uniformly on the interval AB, okay, there is a capital N, so that for all n greater than or equal to capital N and for all x in AB, we have this mod fn of x minus fx is less than epsilon by 3. This is the first equation. Next, since for this n, since fn is continuous at x naught, okay, there exists delta positive so that for all x in the interval a b, so that mod x minus x naught is less than delta implies mod fn of x minus fn of x naught is less than epsilon by 3. This is 2. Okay. Therefore, for every n greater than, okay, let me just see. Therefore, for all x in AB, so that mod x minus x naught is less than delta, we have mod fx minus fx naught is less than or equal to mod fx minus f1 of x plus f1 of x minus f1 of x naught plus f1 of x naught minus f of x naught. Yeah, but this is less than epsilon by 3 by one circle. This also less than epsilon by 3 by the first, and this is less than epsilon by 3 by 2. Therefore, this is less than epsilon. That's it. Proof is over. You see that? Now it's easier to memorize this kind of proof. So you think mathematics must be learned by heart. It's not discovered on our own. How your proof is discovered, how much of thinking went ahead. All those things are swept under the rug. Yeah. So with this, I stop the lecture. Okay, there are a few more applications, but one of time I will stop because tomorrow I want to talk about another important tool on analysis. So if you have gone through analysis course, you found it was very mysterious why the proofs worked, went the way it went, or the way explained the way it is. These three things will help you to have some kind of an anchor. With this, you can go and understand. And if you have a copy of my book, I'm sure your library may have a copy of my book. Please go through these things and you'll begin to enjoy analysis. Okay, because analysis is much among what you call a feared subject for students, but it's very beautiful if you learn to think. It's not purely checking line by line proof. Okay, I'll keep quiet. If anybody has any questions, okay, you can raise hand and then ask your questions. I will clear. I will try to answer.